Welcome students. I am R.D. Patil. I prepared some video lectures on physics for 12th standards. If you like this video, subscribe to my YouTube channel and give the comments on comment box. Yesterday, I explained some primary concepts or some concepts and applications of the horizontal circular motion. That concepts are: first concept, first application is the motion of a vehicle along curved horizontal road. Second applications, motion of a vehicle in vale of death. Vale of death. These applications can be explained already. Now today I am going to explain the motion of the vehicle on curved bank road. Before explanations of this, we must know some primary concepts of bank road. What is meant by bank road, angle of banking, and why is it necessary? These 3 points must be necessary before explanations of that applications. Bank road or banking of road means when the outer edge of the road surface, when the outer edge of the road surface is higher level than the inner edge in such a way that the road surface at curve makes some suitable angle with the horizontal. Such arrangement is called the banking of road or banked road. In these diagrams, here OA is the road surface, OX is the horizontal surface, and the curve is towards the left side. Here the outer edge is higher level than this inner edge. Such an arrangement of the road surface making an suitable angle with this horizontal surface. Such an arrangement is called the banking of road, and the road at the core is called the banked road. Here the angle theta is made by the road surface OA with this horizontal surface OX. This angle is called the banking angle or angle of banking. In next figure or next diagrams, next pictures, here a bank road is given. Here the outer edge is higher level than this inner edge. This is the bank road. This is the bank road. This bank road generally constructs on the national highway at the course road, at the position of curve. Why is it necessary? Now I explain it here. When a vehicle is turned on horizontal curve road, at that time the necessary centripetal force is provided by the force of friction between the tires and road surface. That force of friction is not reliable in every season, as well as when oil is dropped on that road surface. In rainy season, the force of friction is reduces. So the speed limit is given at the road is not reliable in rainy seasons. Also, when oil can be falls, at that time the road surface becomes slippery. Also, the force of friction is not remains constant as the road surface is not uniform. Somewhere the road surface is more rough and somewhere the road surface will be smooth or polished. So the force of friction is not remains constant, and for that purpose the speed limits for the horizontal road surface is not remains same for every vehicles also. Hence, the banking of road is necessary. During this banking of roads, in this banking of road, the speed limit is not depends on the force of frictions, but it depends upon the angle of banking as well as the radius of curved road surface. That can be explained now. To explain these applications, some points can be remembered how to explain these applications. First point is remember that the figures or diagrams. The diagrams is represents here, that is the section of this vertical section of the curve road here given. Here dotted lines indicates the horizontal surface, continuous lines indicates the road surface. Here theta is the angle of banking, and this is the vehicle which travels along the banked road. The turn is toward the left side. Left side the turn say outer edge is higher level than this inner edge. This is the bank road. On this bank road, now explain here explanations of this from the diagrams. Consider a vehicle, this is the vehicle of mass m, moves safely with the speed v along the curved bank road of radius r, if the radius is r, which is banked at an angle of theta with the horizontal. This is the explanations. This is the first point to remember how to explain these applications. Second point is forces on the vehicles. How many forces will be acts now on it when the vehicle is on the curved bank road? First is its weight. Its weight mg. Its weight mg acting vertically downward direction. Acting vertically downward direction. Second force is normal reaction force. Second force is normal reaction force, which is perpendicular to the road surface. Road surface lo perpendicular hai. This normal reaction force. Now third point is remember the normal reaction force can be resolved. Resolution of the normal reaction force. The normal reaction force can be resolved into two rectangular components, which are n cos theta. This is the one component of normal reaction, that is n cos theta is the vertically component which balance the weight of a vehicle, and another component is n sin theta. N sin theta, this is the horizontal component. This is the horizontal component, and its direction is toward the center of the curve road. Hence this component provides the necessary centripetal force. This component provides necessary centripetal force. This is the third point. Fourth point should be remembers the equations. Now n cos theta balance the weight, therefore n cos theta is equal to mg. This is the first equation. And n sin theta provides the necessary centripetal force, that means the necessary centripetal force is equal to mr omega square or mv square upon r. This is the second equation. Now equation second divided by equations first, we get n get cancelled. Sin theta upon cos theta is tan theta. Tan theta is equal to here mr omega square divided by mg. We get r omega square upon g, or mv square upon r divided by mg. We get v square upon rg. This is the tan theta. From this equation third, we gives the equations v square is equal to rg tan theta, or omega square is equal to g tan theta upon r. Therefore, linear speed at the core road surface, this is the maximum speed, v max is equal to square root of rg tan theta. This is the linear speed, and angular speed omega is equal to square root of g tan theta upon r. These are the expressions for the velocity or speed of a vehicle when safely driven along the curved bank road. Curved bank road. Now, this speed is the most safe speed for particular given road of radius r and angle of banking theta. For the fixed for particular given road r, that is the radius of curved road and angle of banking are fixed. Thus, from equation third, v is equal to square root of rg tan theta. This is the most safe speed for the curved bank road. Also, from this equation third, the angle of banking while construct the road at the curve for the given speed, if the speed is given and to construct the road at curve, what is the angle is necessary, that expressions can be found out from the equation third. From equation third, theta is equal to tan inverse of v square upon rg if the speed is given. Speed is given and radius is also given. At that time, the angle is necessary is equal to tan inverse of v square upon rg. On these articles, the question will be asked like this: explain the motion of a vehicle on the curved bank road and obtain the expression for angle of banking, or obtain the expression for the maximum speed of the vehicle for the given angle of banking and given radius of curvature. These are the questions to be asked on these articles. But in practice, all the vehicles on the same curve road cannot travel with this speed. Some vehicles travels with this small speed, some vehicle travels with maximums with large speed than this most safe speed. In that case, what will be happens? That gives the speed limit, minimum speed and maximum speed. Minimum speed and maximum speed limit is must be necessary at the core road surface, and in that case, at that time, we consider the force of frictions. Here, in these articles, we cannot consider the force of frictions. To explain the speed limit, we consider the force of frictions. In next slides, I explain the motion of vehicle on the core bank road with the speed limit, with considering force of friction. Here, in left side's column, we explain the lower speed limit of the vehicle And on the right sides here, I explain the upper speed limit, that is the maximum speed limit. Same curved bank road here is given in both the cases. In both the cases, if the speed of vehicle is small than the most safe speed, we obtain the expression for most safe speed is square root of rg tan theta. If this vehicle having the mass m safely along the curved horizontal road of radius r with the speed v1 which is less than most safe speed, त्याच्यापेक्षा जर कमी असेल, सेफ स्पीड पेक्षा जर कमी असेल, at that time the vehicle slips down. The vehicle slides down on this inclined road surface. So the motion of the tires on the road surface is towards the inner side, and due to that, the force of frictions will be exerted along the road surface, but along upward sides. This is the force of friction. This is the force of friction. This force of frictions arises due to the motion of vehicles slide downs when the speed is smaller than the most safe speed. In that case, at that time, the total forces acting on the vehicles are its weight acting vertically downward directions, normal reaction force, and force of static friction between the road surface and tires. The normal reaction force can be resolved here. The normal reaction force can be resolved into two components, n cos theta and n sin theta. We have already explained in the earlier slides. Here, the force of static frictions also can be resolved into two rectangular components. One is horizontal component Fs cos theta and another is Fs sin theta. This is the resolutions of N and Fs. Now, the net forces acting on these vehicles are the net force acts on the vehicle toward the center of the core road is N sin theta minus Fs cos theta in the diagrams here. Toward the center, this is N sin theta and this is F cos theta. Therefore, the net force toward the center for safely driven the vehicle along the core bank road. Core bank road कडे जर समजा मोशन मध्ये जर जायचं असेल तर centripetal force is necessary, and that centripetal force is always toward the center. Hence, the n sin theta here is larger than the Fs cos theta. Therefore, the centripetal force is provided by n sin theta minus Fs cos theta. Fs cos theta, which provide the necessary centripetal. And the net force act on the vehicles in upward directions. Here, due to normal reactions, vertical upward component is n cos theta. Due to force of static friction, the vertical upward component is Fs sin theta. This vertically upward component is n cos theta plus Fs cos theta. That balances the weight. The net force act on vehicle on upward directions, which balance the weight of vehicle is n cos theta plus Fs cos theta. That can be written in the equation forms like this: n cos theta plus Fs cos theta is equal to mg, and n sin theta minus Fs cos theta is equal to the centripetal force. Here v1 is the speed, therefore mv1 square upon r is the centripetal force, and that can be provided by this n sin theta minus Fs cos theta. Now equation second divided by equations 1, we get n sin theta minus Fs cos theta upon n cos theta plus Fs sin theta is equal to V1 square upon Rg. But force of static friction is mu s into n, we already studied in the 11th standard, where mu s is the coefficient of static frictions. Therefore, the above equation becomes V1 square upon Rg is equal to n sin theta minus mu s into n cos theta upon n cos theta is equal to mu s n sin theta, and that is equal to n cos theta into bracket tan theta minus mu s. Cos theta is common. N cos theta is taken common here. Therefore, here sin theta upon cos theta, that is tan theta, divided by n cos theta into bracket 1 plus mu s tan theta. N cos theta get cancelled. Therefore, V1 square is equal to Rg into bracket tan theta minus mu s upon 1 plus mu s tan theta, and this is the minimum speed. Therefore, V1 is equal to V minimum is equal to square root of Rg into bracket tan theta minus mu s upon 1 plus mu s tan theta. This is the minimum speed limit on the curved bank road with considering the force of friction. Now we explain this upper speed limit. This is here upper speed limit when the vehicle is moves along the same bank road with a speed larger than the most safe speed. At that time, the vehicle slips toward the outer edge. When the speed is higher than the most safe speed, at that time vehicle moves or slips toward the outer edge. So the force of frictions will be arise toward the inner edge along this bank road, And here the force of friction can be resolved into two components, like the normal reaction forces. Same explanations here, but only the speed is higher than the most safe speed. Same explanations about the forces on the vehicles, only the difference is that the force of static frictions is toward the inner edge when the speed is higher than the most safe speed. In this case, in this lower speed limit, when the speed limit is less than the most safe speed, at that time the force of frictions is toward the outer edge on the road surface, along the road surface. That is only difference. Now, the components n cos theta, n sin theta here are the components of normal reactions, and here the fs cos theta, fs sin theta are the components of this coefficient of static frictions. Here, the horizontal component of normal reaction is n sin theta, and horizontal component of force of static friction is fs cos theta. That's both are along the same directions and toward the center. Therefore, the combinations of these two forces, n sin theta and fs cos theta, provides the necessary centripetal force. And vertical component of normal reaction is n cos theta, which is vertically upwards, and vertical component of force of static friction is downwards. Therefore, the net force is n cos theta minus fs sin theta, that balance the weight. That can be explained in the next slides here. The net force acts on a vehicle toward the center of core road is ns sin theta and fs cos theta, which provide the necessary centripetal force, and the net force act on a vehicle in upward direction, which balance the weight of vehicle is n cos theta minus fs sin theta. Fs sin theta is vertically downward directions and n cos theta is vertically upwards, and weight is downwards. Therefore, vertical upward force total net vertical upward force is n cos theta and minus fs sin theta that balance the weight. This can be written in these equations and solve these equations to find out the V2 square, and the V2 is the maximum speed. This is the expressions for the maximum speed. Similarly solve it just like as this lower speed limit. Only the difference is here n sin theta in lower speed limit n sin theta minus mu s n cos theta fs mu s n cos theta that provides the centripetal force, and here n sin theta plus mu s n cos theta provides the centripetal force. Plus signs here, plus signs here, minus signs here, minus signs and plus signs is given. We have learned this articles, similar articles, only the difference is the direction of the force of static frictions here. Now in this, if the coefficient of static frictions is 0, that means there will be no frictions. No frictions. Frictions are necessary. What will be happens? This mu s is equal to 0. This terms is 0. Therefore, the bracket here is tan theta. Therefore, V minimum is equal to square root of Rg tan. Also, maximum speed is also square root of Rg tan theta. That means square root of Rg tan theta. This is the most set speed of a vehicle when it drivens along the curved bank road. Remember this thing. In this expression, there will be no frictions. No force of static frictions is necessary. Hence, the banking of road is necessary. Remember these things. Okay. Next applications, that is conical pendulum. Before I explain conical pendulum, we must know what is meant by pendulum. Pendulum is nothing but a small tiny spherical body. Small tiny spherical body we assume to be point mass, suspended by long, flexible, massless, which have massless, negligible mass, inextensible, not stretchable string from a rigid supports. From a rigid support. This is the rigid supports. Such arrangement is called the pendulum. Such arrangement is called the pendulum. That is called the pendulum. When this pendulum moves with some angle from its mean position, this is the mean positions. This is the mean position. And when we displace through small angle toward these positions and released it, at that time, that pendulum performs oscillations. Performs oscillations like this from B to C, C to B again. This is called the simple pendulum. When the pendulum moves to and fro in such a way that the string oscillates in a single vertical plane, then the pendulum is called the simple pendulum. The distance between the center of gravity of the pendulum to the rigid supports, that distance is called the length of simple pendulum. Length of simple pendulum, remember this thing. Now, here we doing study about the conical pendulum. Conical pendulum means when the simple pendulum or when the pendulum displaced through some angle from its mean positions, like this angle, and give the horizontal velocity, in such a way that it performs a horizontal circular motions and forms a cone-like structure by the threads. Then that is called the conical pendulum. If the pendulum is displaced through small angle from its mean positions, gives the horizontal velocity to the bob in such a way that the bob performs uniform horizontal circular motions and string moves along the surface of right circular cone, then the pendulum is called the conical pendulum. This is also the example of the horizontal circular motions, uniform horizontal circular motion. Conical pendulum performs horizontal circular motions. And the string stress a conical surface, hence that is called the conical pendulum. In these articles, in these applications, we can find out the period of oscillations or frequency of oscillations of conical pendulum. Here also points can be remembered by using this 4 points figure and explanations, forces on bob, resolution of forces and equations. These are the 4 points. Here, this is the first diagrams. This is in inertial frame of reference and this is in non-inertial frame of reference. Second diagram is in non-inertial frame of reference. When a pendulum displaced through small angle theta, angular displacement, and give the horizontal velocity in such a way that it performs this horizontal circular motion. Horizontal circular motion. At that time, here the explanations from the diagrams is given. Assume that a conical pendulum have a heavy metal bob considered as the point mass of M is suspended by flexible string, flexible, weightless, inextensible string of length L. Now this is displaced through some small angle theta with its vertical axis, that is also called the semi-vertical angle of cone, gives horizontal velocity. At that horizontal velocity V, at that time it performs the horizontal circular motions. This is explained from the diagrams. At any position B, this is the any positions in this circular motions. At this positions, the forces acting on its are its weight, mg, acting vertically downward directions. This is the weight, acting vertically downward directions. And tension T0, produced in the string toward the point of suspension, This is T0. This tension can be resolved in third points here, resolution of force. This tension force can be resolved into two rectangular components. One is T0 cos theta, which is vertically upward components, and which balance the weight mg, of the pendulum. And another component is T0 sin theta, which is toward the center of this horizontal circular motion, that provides the necessary centripetal force. Therefore, equations are T0 cos theta balance the weight, that is mg, T0 cos theta is equal to mg, and T0 sin theta is equal to mr omega square, or it is equal to mv square upon r. This is the centripetal force. Now equation second divided by equation first, we get tan theta is equal to r omega square upon g, or v square upon rg. Here T0 sin theta upon T0 cos theta means tan theta, mr omega square divided by mg, that is r omega square upon g, or mv square upon r divided by mg, that is v square upon rg. From these equations, V square is equal to Rg tan theta or omega square is equal to G tan theta upon R. Therefore, the speed V is equal to square root of Rg tan theta. This is the fourth equations, or angular velocity is equal to square root of G tan theta upon R. From these equations, period of conical pendulum is the circumference, the length of circumference upon tangential velocity twice pi r upon v, or angular displacement, that is angular displacement of this particle is twice pi and angular velocity is omega. Therefore t is equal to twice pi r upon v, or that is equal to twice pi upon omega. And from this twice pi r upon twice pi into square root of r g upon tan theta, this is the expression for the period. If we substitute the value of omega as square root of g tan theta upon r, here that is the expression twice pi r upon g tan theta. If we substitute the value of v in these equations, at that time r get cancelled, here one r is remains. This is the same expressions will be obtained. This is the expression for the period. Here, 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 r is equal to, here r is equal here r is equal to, I can be explained here from this diagram. This is the radius, this is the radius, this is the radius here. Okay, okay. Here from these diagrams, this is the radius, and sine theta is equal to r upon L. That means r is equal to L into sine theta. Substitute the value of r as L sine theta. L sine theta upon g tan theta. Tan theta means sine theta upon cos theta. Cos theta goes on numerator. Sine theta can be cancelled. Therefore, here twice pi into square root of L cos theta upon g. This is the expression for the period of simple pendulum. Period of simple pendulum. This value of r can be determined by using this right angle triangles from point of suspension to the center toward the position of the particles. From this right angle triangles, we can find out the value of r. R is equal to L sine theta, where L is the length of simple pendulum. And after substitutions, we get twice pi into L cos theta upon g. This is the period of simple pendulum, and frequency of, sorry, this is the period, this is the expression for period of conical pendulum, not a simple pendulum, period of conical pendulum. And therefore the frequency of conical pendulum is equal to 1 upon period, that is the reciprocal of period, and that is equal to 1 upon twice pi into square root of g upon L cos theta. This is the expressions. On this, in these articles, we can here in these articles, questions will be asked like this: explain the conical pendulum and obtain the expression for the period or frequency of a conical pendulum. Frequency of conical pendulum. Now we stop here. If we like this video, If you like this video, subscribe to my channel RD Patils and give the comments on the comment box. Thank you for watching.